You ever wonder how your car insurance premium gets calculated? Or how Google just knows the next word you're about to type? Well, the answer is a really powerful mathematical tool called the Markov chain. And I know it sounds complex, but at its heart is a surprisingly simple idea. What if the future only depends on the present? Let's find out how that's even possible. So here's our game plan. First, we'll tackle that core concept, the memoryless predictor. Then we'll see how it works in the real world with car insurance. After that, we'll lay out the rules of the game and see how this tool lets us predict things way into the future. And finally, we'll look at where else this stuff shows up and wrap it all up with why it matters. All right, section 1, the memoryless predictor. We're going to start with a really strange, almost counterintuitive idea. What if everything that's ever happened before just doesn't matter for what happens next?
I mean, think about it. Can you really predict what's coming next using only what you know right this second? Our gut tells us we need the whole backstory, right? The whole chain of events that got us here. But what if all of that history is just, well, noise?
This is the core concept right here. It's called the Markov property, and it says that the future is independent of the past given the present. In a Markovian system, the only thing that matters for the next step is where you are right now. The entire journey you took to get here is completely irrelevant. So yeah, welcome to the world of memoryless models. By just ignoring the past, we can simplify these incredibly complex systems. It sounds weird, I know, but let's see how this powerful idea works with something you probably deal with every single year. Which brings us to a perfect real-world example, insurance. Specifically, that no claims discount or NCD you get on your car insurance policy. It turns out this is a textbook case of a Markov chain in action. Okay, let's build a simple model right now. Imagine a driver can only be in one of 3 states. You've either got a 0%, a 25%, or a 50% discount. And we'll just make one assumption. The chance of having a claim-free year is a pretty solid 75%, or 3/4. Now, the rules for moving between these states are super simple. If you don't make a claim, you move up a level, or you just stay at the top. If you do make a claim, which has a 1 in 4 chance, you move down a level or stay at the bottom. See? Your discount next year only depends on your discount this year, not your driving record from 5 years ago. It's totally memoryless. So we've got our states and we've got our rules. But how do we turn this simple logic into a powerful predictive tool? Well, that brings us to section 3, the rules of the game, where we're going to build the engine for our predictions. We can actually map this whole system out in what's called a transition graph. Each circle is a state, so a discount level, and the arrows show the odds of moving between them. For instance, if you're at state 1, the 25% discount, there's a 3 in 4 chance of moving up to state 2, and a 1 in 4 chance of dropping back to state 0 if you make a claim. This is a complete visual map of every possible outcome. And that visual map, it translates perfectly into this table, which is really the heart of the model, the transition matrix. You can think of this as the system's complete rulebook, all in one place. Just look at the first row. If you're in state 0, it tells you there's a 1 in 4 chance of staying put and a 3 in 4 chance of moving to state 1. It contains all the rules from our diagram right there in the numbers. Now, there's a really key rule hidden in here. Notice how each row adds up to exactly 1, or 100%. That's because from any given state, something has to happen. A transition must occur. Even if that transition is just staying right where you are. You always have to land somewhere. Okay, so this takes us to section 4, predicting the long term. Because that simple matrix we just saw, it holds some incredible power. It's not just a snapshot of 1 year. It's the key to seeing the future of the entire system. And here's where it gets really clever. If you want to know the probability of moving from any state to any other state in, say, 2 years, you don't need to draw some huge, complicated diagram. You just multiply the matrix by itself. That's it. The new matrix you get, p², gives you all the 2-step probabilities, just like that. And this incredible pattern just keeps going. For 3 years, it's p³. For any number of years, let's call it n. It's p to the power of n. This simple, repeatable calculation is our key to peering deep into the system's future. So what happens if we keep multiplying this matrix, looking further and further and further into the future? Well, eventually, the numbers stop changing. The system reaches an equilibrium called a stationary distribution.
Now, this doesn't mean individual drivers get stuck. No, they still move around. What it means is the overall percentage of drivers in each state becomes stable and predictable year after year after year.
So for a slightly more complicated insurance model, this is what that long-term balance looks like. Even with thousands of drivers moving up and down the discount ladder every year, an insurance company can predict with really high confidence that, in the long run, about 64% of all its drivers are going to be in that top discount tier. And that is incredibly useful for managing risk and setting prices.
This is obviously powerful for insurance, but the real magic is just how versatile this memoryless model is. It's a foundational tool that pops up in some pretty surprising places. Which brings us to Section 5, Beyond Insurance.
A classic example is something called the random walk. Now, our insurance model was a closed loop, right? You just bounce between a few fixed states. But a random walk is different. It can have an infinite number of states. Just imagine taking a step left or a step right based purely on a coin flip. Your next position only ever depends on where you are at this exact moment.
And this diagram just captures the idea perfectly. At any point, there's a probability p of moving one way and 1 minus p of moving the other. This incredibly simple model is a cornerstone for understanding things that seem totally chaotic, like the fluctuating path of a stock price, the spread of a disease, or even how molecules spread out in a gas.
So we've gone from a simple idea to predicting long-term outcomes for all sorts of systems. And this brings us to the big question in our final section. Why does any of this matter? What's the big takeaway here? The true power of a Markov chain is this. It takes a messy, complex world and boils it down to just two things: where you can be and the odds of getting from one place to another. It's the hidden engine behind things you use every single day, from how Google's original PageRank algorithm figured out which websites were important to how your phone's keyboard predicts the next word in your sentence. It's proof that sometimes the best way to see the future is to focus entirely on the present. And that leaves us with a final question to think about. We've seen it in insurance and in random walks, but what other complex systems in economics, in nature, in our own societies might look chaotic on the surface, but are actually governed by simple, memoryless rules, just waiting for us to discover them?